I welcome you all to another video tutorial session on finite element procedure for solving structural engineering problems. In this video session, we are going to look at how we can analyze a beam problem with the Ansys program using 3D finite elements. In my previous video, I cover analysis of a beam problem with the one-dimensional finite element and also with the two-dimensional finite element. That is using plane stress condition under the two-dimensional finite element procedure. In today's video, we are going to analyze this problem using the 3D finite element procedure with the Ansys program. So this is our problem. The problem is a two-span continuous beam with structural loads on the two span as shown. And once the first span is 7 meters, the other span is 11 meters. We're told that at the middle support C, we have a 4 mm settlement, and the material and the geometric property of this beam problem is defined by this quantity here, EI. Say EI equals to 100 times 10 power 3 kilonewton meter square. The EI is a term called flexural rigidity in structural engineering. So you may refer to EI as flexural rigidity. So the flexural rigidity EI is equals to 100 times 10 power 3 kilonewton meter square. The EI is a product of the Young modulus and the moment of inertia. The E represents the Young modulus, while the I represents the moment of inertia. So we're given this to define the geometric and the material property of this problem. In my previous video on this same problem, and using the one-dimensional and the two-dimensional analysis, I explained how we decompose this EI into the Young modulus E and the moment of inertia. I have a slide for that. Let me show you. So given that the EI is this, we made an assumption that the E is this value. So given that, assuming E equals to 205 kilopascal, we can compute I, the moment of inertia. So EI equals to this. If we substitute this E into this equation here, we get I equals to this value. We get I equals to that value. And the value will be in meter raised to power 4. Now we made another assumption that our cross section for our beam is a square. So assume a cross section is a square of length times length. So the moment of inertia formula will be L over 4 divided by 12. If we equate this L over 4 divided by 12 equals to this value here, which is here. So we get L equals to this value, 0.2766030 meters. I'm working in millimeter. So I multiply this value by 1000 to get the value in millimeters. So this is 276.60293 millimeters. So this is the explanation. I'm going to use this parameter, the E value and this L value, when I'm defining the geometric and the material property on the Ansys program. So that's just a quick overview of how we determine the E and I from the flexural rigidity. Before I jump to the Ansys program, I would like to explain some few concepts in 3D finite element procedure. I have a PDF here. So this is a PDF, and in this PDF you see different 3D finite elements. You will see I'm coming to go to I have a pen here, okay. So we see different 3D finite elements. So our 3D finite element can either be a tetrahedron of this shape is 4-noded, or an hexahedron is 8-noded, or a pentahedron which is 6-noded, or this tetrahedron, which has 10 nodes, is actually the same, but at each at each edge at the middle, we have extra node. So if we should add everything together, we get 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's why this is 10 node. That's why this tetrahedron has 10 nodes. So the tetrahedron can, let's say, can be linear or quadratic. 3D element which has inner node, let's define it as quadratic 3D finite element. So the 4 noded is linear, the 10 noded is quadratic, I'll call it quadratic 3D tetrahedron finite element. This hexahedron, which is 8 noded, can also be 20 noded if we assume each edge has also middle nodes. So if you add everything together, you get 20 nodes. This pentahedron here, which is 6 noded, if we assume there is also extra node at each edge, the pentahedron below here will be equivalent to 15 noded. So these are some 3D finite elements which we can use to analyze a structural engineering problem. So I just want to show you how this 3D finite element looks like. It can be tetrahedron, it can be hexahedron, it can be pentahedron. I don't know if there are other shapes, but these are the 3 common shapes that I know about. So this is a quick overview of what the 3D finite element is all about. So now we are going to move to the Ansys program. We are going to now we're on the interface. We are going to activate our static structural solver for our 3D analysis. As you can see, I have three structural solver here. The first one is for 1D analysis. The second one is for 2D analysis. These two I did in my previous videos. So the one I'm doing today is for the 3D beam analysis. The 3D beam analysis. Okay, so before I start, I will change the name of this structural solver to 3D analysis. So the first thing we're going to do, we're going to move through each of the workflow from engineering data to results. So I will double click on the engineering data to enter my material property for the beam problem. So I'll create a new material, I'll call it steel. Once you have done that, you only need to add a property to this steel, which is enough. So the property is under the linear elasticity, the isotropic elasticity. You drop it on the steel. As we see in our PowerPoint, our Young modulus is 205 gigapascal. So we enter the value for Young modulus here. Change the units because I'm entering the value in gigapascal. I have to change this unit to gigapascal and enter the value 205. This portion ratio, let's assume is 0.3. It does not really affect the accuracy of the result that much. We are not giving, but we're assuming it to be 0.3. So we're done defining the material property of our problem now. Just with this, we can close this window now. We'll move to the next workflow. Under the geometry, since we are using solid bodies for our 3D finite element, so we don't need to activate this line body. We only activate this line body when we're analyzing in 1 dimension. So we don't need to check this, but you can check it, but we don't need to check it. Under the analysis type, this analysis type should be set as 3D, very important. So on the static structure solver for the 3D analysis, I will double click on the geometric number 3 workflow, the geometry. I'll double click on it to open the space claim working environment where we define our geometric property, the shape of the beam, the length, and the cross section of the beam in 3D. Now the space claim working environment is active. We will sketch our beam. How do you want to sketch our beam? I will choose the XY plane. So I'll click on this button. Click on this button, and you move your cursor to this position until the XY plane is selected. So you click on it, bring it to view. So I'm going to draw my cross section of the beam in this plane. And if we go back to our PowerPoint, remember the cross section of our beam is given by this value. L equals to 276.60293 mm. This is a square, so the length and width is equals to this value. I already have the value calculated here. You see the value here. So I'll just copy this value. Copy that value, go back to space chronological environment. You click on the rectangular button here under the create panel. Click on the rectangular button. Put your cursor on the 0, coordinate and draw a square. On the first dimension, enter a value. Press backspace to remove that value and paste what you copied from the calculator by pressing Ctrl V on your keyboard. Don't press enter. Press tab to move to the second dimension and enter a value there, like 1. Backspace to remove it, Ctrl V to paste, and enter. So this is our square section for our beam. So we can end our sketch. I will end our sketch. But if we end the sketch, you will see coming. I'm trying to I hold down my scroll button and I twist to rotate the view in this direction. And if I should bring my cursor to this rectangular plane shape, you will see I have the ability to pull it, but by how long will I pull it? That value is given. The overall length of our beam is 7 plus 11. That's 18 meters. So I'm going to pull it 18,000 millimeter. 18 meter is equivalent to 18,000 millimeter. I'm going to pull it 18,000 millimeter. So I click on it, I drag, I enter the value 18,000 and I press enter. So this is my 18,000 millimeter beam. You should go back to the PowerPoint. It's advisable to create edges at every salient point along the beam. Like at salient points, like on this beam problem, are point A, point B because there is a point load there, point C because our uniformly distributed load ended at C or we have a reaction at that point, point D because we have a point load at this point E because we have a point C load at this point, and point F also because we have a reaction force at that point. So we have to create edges at the top and bottom at this point. So at point B, I'm going to create an edge at the top of the beam. Also at point D, I'm going to create an edge at the top, and at point E, I'm going to create an edge at the top. Let me show you how to do it. So point B is 3 meters from A. So I'm going to create an edge. I'll show you how I'm going to do it. I'm going to use the split body zoom. We are taking this point as our the start of our beam. We're going to use the split tool. We're going to select the top, and we're going to remove your cursor. You'll see, and the split tool helps to split surface on a 3D body. So if you press tab, you can either enter where this split should be defined, either in percentage or in length. But since we know the length, so we'll press tab to move to the second dimension, and we enter 3 meters. We know B is 3 meters from A, 3 meters, that is 3,000 mm. So you see the first edge has been created. Second edge, let's check our PowerPoint. The second edge at the top at node D, point D is how many meters from B? Point D is 4 meter plus 3 meter from B, so that is 7 meter. So I'm going to create another edge 7 meter from B, 7 meter from B. Click on split, select the surface you want to split. So move your cursor. Once you do that, press tab, enter 7,000 mm, enter. So the second edge has been created. What again? We have E. We have E, and E is 5 meter from node D. So I'm going to create this edge 5 meter from node D. So do that now. So okay, I'm still on the split tool. I'll select the surface 5 meter, tab 5 meter, 5,000 mm. So I'll split the top to cater for the load which I want to apply on the surface or the edge at the top. So we have to do the same thing for at the bottom for the reaction forces. Let me erase all this so it will be clearer. So at the bottom, we have to create an edge to define this point, because we will specify our support reaction at that point. So we have to create an edge at position C, and that edge is 7 meter from A. That's actually the only edge we need to create at the bottom. So I'm going to create an edge 7 meter from A. So what you need to do, hold down the scroll tool on your keyboard and pan your mouse until you see the bottom of the beam, and you click on the split tool under the intersect panel at the top and select your bottom plane, and you will see that you can specify, press tab to go to the length dimension and enter is it 7 meters? Yeah, 7 meters. 7 meters. So you see let me zoom out. You can see the edge has been created and the surface has been divided into two portions. You can see. So I'll click on the escape to leave the split tool. Now let's click on this 3D button here. Now we have specify our geometry on the space clean working environment. That's actually all we need to do on the space clean working environment. We can close this tool now. I close it and go back to the workbench working environment. So I've defined the geometry, move to step 4, the model. We double click on it to open the mechanical workflow, where we specify the boundary condition, the meshing, the structural load, and we view our result in 3D. So let's see how that is done. Now the mechanical interface is active. Let me check the geometry. You see we have one solid body, material steel, structural steel. That's what we have. So we should change our 3D body. We defined a material at the beginning of the video, the steel material we define. So we have to change this material assignment here from structural steel to what the material we created, which is steel. So having done that, we'll go to the mesh. What we can do here, we can specify method and sizing, but you can only do sizing if you want, but I want to use this too. So I'll specify the method first. Method, I'll click on this body, the solid body, I will apply to that. Element order, linear, you see, linear. For the tetrahedron, which has 4 nodes, that is linear. The tetrahedron which has 10 nodes is quadratic. For the for the hexahedron, which has 8 nodes, this is linear, and for the hexahedron, which has 20 nodes, this is quadratic. So the top, this finite element at the top is linear, the one at the bottom is quadratic. So that's what we have here. So we can either set this to linear or quadratic, but I'll set it to quadratic because I need more accuracy. So I'll set it to quadratic. I'm giving the software more work to do. I will set the finite element order to quadratic. The method, you can see we have tetrahedron, we have X dominant. But I'll leave it as automatic. Let the software decide on the best finite element to use. I'll leave it as automatic. So under the mesh, we have defined the method. Method is the type of finite element we want to use. We are using a quadratic finite element, but I set it as the type of finite element I set as automatic. So the software will choose either it's hexahedron or hexahedron or pentahedron. That is the software will decide that for us. So under the mesh insert, click on sizing to determine the size, to specify the size of our 3D finite element. And you need to specify the geometry. Select the geometry with your mouse and you click on apply here. So I've select the body and the and this selection has been applied to this body sizing. Element size, let's define it as 100 mm. 100 mm, element size 100 mm. So let's mesh this problem and see how and see the finite elements we get. Oh, 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 the finite element. Okay, let me choose finite element. So the finite element is an hexahedron finite element. The software use uh, an hexahedron 3D finite element to model this problem. I'm trying to make pan. So we see it here. If you should select this element, I want to see if you can select node. See, you can see it has a middle node because it is quadratic. It has middle node, which is beautiful. So we're using we are using quadratic hexahedron 3D finite element to solve this problem. So now we have defined the mesh. We move to the static structure and we define our boundary condition. We're going to use displacement support. In our problem, in our PowerPoint, we have a pin support at this position. So x and y is 0. We restrain movement in the x and y direction. So I've created a support. Let me zoom this, put this down. So I'm going to make sure you're on the edge. You're using the edge selection tool. Pan, edge selection tool. Select this edge and apply this displacement support to that edge. So support has been applied to that edge. So because this beam was drawn in the the beam is drawn in the YZ direction. So I'm going to restrain the Y and Z direction to 0. So the Y will be 0, the Z will be 0. The X will be free to move, Z will be free to move. So that's for that support. At the intermediate support, at C, we have a roller support. So the Y restraint is 0. So I'm going to duplicate this support. Duplicate. You zoom out. Hold down your scroll button on your mouse. Yeah. I don't know what I'm doing again. Okay. Hold down your scroll button on your mouse until you see the underneath of your beam, and I need to select this edge. Make sure you are using the edge, you're on the edge selection tool and select this edge. Displacement tool, apply the support to displacement tool. Y the restraint is 0, Z should be free. So set Z should be free. Just Y is 0. At the end support, we also have a roller support. That is restrained in the Y direction. So I'll duplicate this support, duplicate, pan, select this edge, select this edge. You have to be on selection tool, select this edge, apply that selection to displacement 3 support. So just restrain in the Y direction is always set to 0. The others are free, which is what I want. So I've defined the support boundary condition now. Click this ball to come back to 3D, isometric view, 3D isometric view. You can select this support boundary condition and group them. Return the folder where they'll be grouped as supports. Let's specify the load on the beam, on top of the beam, static structural insert. And this is what we use to specify the loads. Force, click on force, and we check our PowerPoint. We are defining the load. We're going to define this portion of the load first, this span first. Then we will define this span second. Then we define this one separately, this one separately, this one separately. So for this first part, this first part, that is span AB, and we have a 12 kilonewton per meter load on the span. So the total load in kilonewton will be 12 kilonewton times 3, 10 kilonewton per meter times 3, which will be 36 kilonewton. Per meter, it is 12 kilonewton. 3 meter will be 36 kilonewton. So we are going to apply 36 kilonewton load on this span. So that's what I'm going to do. But on the Ansys program, okay. So that means, and the application of the load will be applied on surface, not edges, like the 2D plane analysis. So I'm going to select the top surface, and I'm going to apply select this force and apply that force to that surface. Defined by components. So the force can see is in Newton. I cannot define it in kilonewton. So we calculated 36 kilonewton force. So in the Y direction, we're going to enter minus 36 Newton, minus 36,000 Newton force. Minus 36,000 Newton force. Minus because the load is pointing downward. So minus 36,000 Newton. So that's the first load on the first span. On the second part, oh, I made a mistake. I made a mistake. I made a mistake. I made a mistake. B. I didn't define this edge. I didn't define the top edge at this point. So I'll quickly go back to my space claim to define the edge at this point, because the next edge I'm seeing is at this point. So I'll quickly go to space claim to define the edge. So let's close this window and go to the space. Let's open another geometry, double click on it to open the space claim. We need to create it's not actually a mistake, I omitted something. We need to create an edge at this point, that is an edge at point C, 4 meters from B. I didn't create that edge. So let's create that edge now. 4 meter, 4 meter, 4 meter, 4 meter, 4 meter, 4 meter. Okay, I'll do that now. So I'm going to use the split command quickly. Let's not waste time. Make sure you're under design tab, intersect, split, select this surface. So press tab, 4 meters, 4000 mm. 4000 mm. Let's look at the PowerPoint again. Okay, correct. So this edge represents the end of my uniformly distributed load here. So I'll close this again to update. So open the model. Update data needs, upstream data needs to be reread. Good. Would you like to read the upstream data? Yes. So the mechanical work environment will open now. While the mechanical work environment is loading, let's see the load we apply on span BC. That is from this point to this point. The uniform distributed load is 12 kN per meter. The span is 4 meters, so the total load is 12 times 4, 48 kN force. So that is 48,000 kN force pointing downward. So 48,000 kN force pointing downward. Let's specify that. See, mechanical work environment is still loading. We'll have to apply 48 kN force on the second portion of the force span. Okay, active now. Still, the material assignment is still good. The mesh still okay. Support still specified properly. This is specified properly. So I will duplicate this first support. Duplicate, but you have to change. You have to apply this force 2 to this surface. So select this surface. Make sure you are on your what they call this face selection tool. So select the surface, force 2. So change the application, the geometric application. So it has been changed. The force 2 has been applied to the second portion of span 1. So you have to change this force to 48,000 Newton, minus 48,000 Newton. So this is minus 48,000 Newton. So after that, we have specified the uniform distributed load on the first span. Let's enter, let's specify, let's specify the 10 kilonewton load at node B at this point, this node. So what we can do here, mechanical tool, we can also duplicate this force 2, force 3, and with the point load we apply on edge. So we need to use the edge selection tool, and this is the edge. Need to pan. Okay. And this is the edge where the load is applied to. This is the edge. The edge is selected now. So geometry, you can see as the edge is selected, the load is you can see the load is 10 kilonewton force. So that is 10,000 Newton pointing downward, minus 10,000 Newton. So that is for that for span 1. We also have 8,000 Newton at D. I'm going to, that's 8 kilonewton, 8,000 Newton at D, and 6,000 Newton at E. So we'll apply that load now. So we can select force 3, duplicate, select, let me pan it, maybe to select the edge tool, select, this is the edge for the load for the 8 kilonewton force. I know that's the edge because I understand my geometry. That's the edge. So I'll apply force 4 to that edge, and I will change this to 8,000 Newton. I will duplicate force 3, force 4, and I will select this edge. I'll select that edge, and I will apply the force to that edge, 6,000 Newton. So that is the force on the top of the beam. So once we have done this, let me run an analysis. Let me see if we don't have any problem with our setup. So this will take like 30 seconds or 1 minute. How do you not able to apply it to prevent engine movement? And this is minor problem. If one is a minor problem, it will not affect the accuracy of the results. Um, we have a problem with our analysis. Let's check the message. Error. The server pivot warning or error has been detected in the US degree of freedom. This is the I think we and using the 3D finite element analysis, we need to restrain rotation. I will do that with a tool now. Let me see if that will solve this error. So static structural insert. We are going to use I don't see what I'm looking for. Remote rotational displacement. So I think let me read the error again. They say a server power error has been in the US direction. So I think we need to restrain this US direction. So let me see our support boundary condition. Displacement support. Our S component is free. Let's make it 0. And let's see if the error disappears. I go analysis again. Gazelle. Now the analysis was successful. So it means that we needed to specify our displacement in at least one point in the three dimension x, y, z. In at least one point, we need to specify the displacement quantity as 0 in the x, y, z direction as 0. So now that the result is the problem has been successfully analyzed, let's view our result. Solution, insert, deformation, directional deformation. We want to see the deformation. We want to see the deformation in the y direction. What can we view again? We can probe reaction, force reaction. So let's the proof of force for the displacement boundary condition is force reaction. Let's duplicate this. We change the boundary condition to 2. Let's duplicate this. We change the boundary condition. Duplicate. Change the boundary condition to 3. We forgot something. Just remember, we have a settlement 4 at support C. So let's specify that is minus 4 downward. So I'm going to specify that now. That is settlement 2. So settlement 2, the y component is not 0 it is minus 4 downward. So I will run analysis to incorporate that 4 settlement at support C. What results can we add again? Still analyzing 5%. Complete. What result can we add again? We can compute our bending moment from our normal stress. So what I'm going to do now, under the solution, worksheet result summary, click on available solution quantity. These are the results we can visualize on the Ansys program. I would like to visualize this is the normal stress. I need to view something actually. Sorry. Normal stress. I need normal stress in the z direction. So solution worksheets available in the z direction. That is xz. So stress in the z direction. Normal stress in this xz is normal stress in the z direction. So I'll create user defined results. I'll need to draw a path to display the for the bending moment result. So click on model, insert, construction geometry parts. You can use part type. You can use 2 points. The first point 1, let's say is at 18 meters, that is 18,000 mm, using the global coordinate system, 18,000 mm. And the second point is at 0, 0. So let's leave it like this. So that's our part. So for this XZ, I'm going to visualize our result using that part, all bodies XZ. As we did in our 2D analysis, I explained something in my 2D analysis. Can see we say that the moment formula equals to the stress sigma multiplied by the moment of inertia divided by y. Y is the distance from the neutral axis of the beam to the top or bottom fiber. So y will be half of this L value. So let me go to the work environment. I want to copy an expression in my 2D analysis. I will open this mechanical work environment for my 2D analysis. So we can copy an expression from there. I don't want to calculate I and Y again. Okay, now the mechanical environment is open for the 2D analysis. This is XX. This is the expression. The XX multiplied by the this value. This value is the moment of inertia. This value is half of the length. Is in meters. The value is in meters, yeah. So measure Newton meter. That's what I'm using. That's why the I is this I is in meter for this I here. This Y here is in meter, linear meter. So I copy this value. I minimize this window. We should have two mechanical environment open. So under the XZ, I paste this value, but this is not X, it is XZ. So enter. So that's for that. So this directional deformation, I didn't use part. I'll create another directional deformation with parts. Directional with parts. I'm using parts so that we can check. You can see the real shape of our deformation body in line diagram. So directional Y. So let's run analysis to view everything. So under directional, let me bring this to view. No. Come. Under the first directional deformation is in the y direction. If I should play animation, you see how the beam is deflecting, and we see that I think it's deflecting the way it's supposed to deflect. And we can see that the maximum deformation in the beam is 5.6291, and we should check our 2D analysis. If we check our 2D analysis for directional deformation, we also see 5.6262. However, we should not actually compare our result with the 2D analysis because it's not that accurate. I will open the mechanical environment for the 1D analysis, which we have done in our previous video, to compare our results with the 3D results. So while this mechanical is running, let's move to other results. So the second directional deformation, in which I use the line part. So let me bring this to you. You can see the deformation shape here. This is this is the mechanical environment for the 1D dimensional analysis. And here we see our directional, the maximum deformation is 5.6272, which is the same thing. Okay, let's put 1D here, and let's put 3D here. So for the first one, so the maximum here is 5.6291 mm. Same thing here, 5.6272. Very, very close deformation value. The for the deformation shape, we see the deformation shape is like this. At 7 meter, at 7 meter, can I get 7 meter? Can't get 7 meter. But someone close to 7 meter can see the value of the deformation is 4 mm, minus 4 mm. You can see this minus 4 mm here. And we also check the 1D analysis. Oh, mistake. Check the 1D analysis, you can see that the deflected shape is similar. Can see the shape is similar. Can see the shape. Can see also the shape is similar. Just because this screen is somewhat bigger than. Let me reduce it. Can see the shape is similar. Can see the shape is similar. Let's go to the force reaction. The force reaction at the start of the beam. We should read tabular data. The force reaction in the y direction is 43,136 Newton. Force reaction, this at the end, this at the middle, at the end. Tabular data, this is 43,138, this is 43,136. You can see the 3D result gives very close answer to the 1D analysis, which is very interesting. For the middle support, for the 1D, we have 61,229. Middle support, we have 61,233. Very, very close. Very, very close. Just 3 Newton difference. For the force reaction at the end, we have 3,633 Newton. At the end, for reaction 3, we have for reaction 2, for reaction 4, we have 3,631. This value and this value. You can see this value and this value, they are very, very close, very, very similar. So what again? The bending. This is the bending moment. This is the bending moment for our problem. Let's use graph. Let's view it graphically. You can see the bending moment. So the 3D analysis is our bending moment diagram. You can see we have 0 bending moment at the beginning. We have a maximum. Let's change it to Newton per meter. We have a maximum bending moment at the span as 75,282 Newton meter. Ignore the Pascal, it's showing Pascal because the result is actually for stress, but the unit is showing is in Pascal. So, but the maximum moment is 75,285 Newton meter. Let's check our bending moment diagram for this problem. Let's change the unit to meter. The maximum is 75,413. Here is 75,235, which is very close. We have 75,235 for the 3D analysis, and for the one-dimension analysis, this value here it is 75,413 Newton meter. At the support, at the middle support, we have a maximum moment of minus 30,087 Newton meter, and in our one-dimension analysis, we have 32,000 Newton, 32,000. This value here minus 32,036 Newton meter, which is still somehow close. 2,000 Newton meter difference. It's not actually correct. It's not actually that correct, but it's similar. The value somewhere here at 10 meters. At 10 meters is we don't know how to check the. We can check the tabular value along the span. So at let me use PowerPoint. At point D, let's check the bending moment. At point D, This is 3 meter, 4 meter, 3 meter. So these are 10 meters. Let's check the bending moment value at 10 meters. For the one-dimensional problem, the bending moment at 10 meters, let's go, the bending moment at 10 meters is 935 Newton meter. Let's check for the 3D analysis. At 10 meters, we don't have 10 meters, but we have something close. We have something close. At 10.125 meter, it is minus 607. While at 10 meter is minus 93.7. So you can see if it's at 10 meter, we'll get something close to this value. We don't actually have 10 meters in the 3D analysis. We don't have the value for 10 meters. We have for so say at 10 meters, it will be close to this value, maybe 800, maybe 900 Newton meter. So this is how we use this is how 3D finite element procedure is applied to beam problem with the Ansys program. So I've come to the end of this video session. In my next video tutorial, I'm going to treat symmetry in beam analysis using Ansys. We're going to analyze this full beam problem, and we're also going to analyze this half beam problem. This half beam problem is actually from this full beam problem. You can see that this full beam is actually a symmetric beam. It's symmetric, geometric, and by loading. When I say symmetric, about this point, the middle, what's on the left-hand side, what's on the right-hand side. So instead of analyzing the full beam, we can just analyze half of it. And analyzing half of it, we're taking, well, it just means that there's no deformation in the direction of the beam, in this direction. And also there is no rotation at this point. So I'm going to explain how this problem, how we can analyze symmetric problem using half model with the Ansys program in my next video. This is going to be the last problem on beam problem. After this problem, I'll move to the frame analysis, and I think I've achieved my goal. After I complete the frame module, I think I've achieved my goal in explaining finite element procedure on YouTube. Thank you so much for watching my video, and I hope you've learned a lot. Have a nice day.